video, we are going to see about BLDC load matching and commutation techniques. This diagram illustrates how a brushless DC motor controller continuously matches the motor output with the load demand by controlling the commutation sequence, PWM duty cycle, and motor current. Unlike brushed DC motors, BLDC motors do not have mechanical brushes. Instead, an electronic controller performs the switching of the motor phases based on rotor position. Proper load matching ensures that the motor produces the required torque while maintaining high efficiency, low temperature rise, and smooth operation. So first one is load and torque requirement. The first block represents this. Different applications require different amount of torque and speed. For example, an electric vehicle climbing a hill requires high torque at low speed, whereas cruising on a flat road requires moderate torque and higher speed. Similarly, a drone experiences varying loads depending on payload and wind conditions. The controller first receives the desired speed or torque command from the user or the vehicle control system. This command determines how much current should be supplied to the motor. The torque produced by a VLDC motor is directly proportional to the phase current. So, torque is proportional to current. Therefore, whenever the load increases, the controller increases the motor current to produce additional torque. When the load decreases, the controller reduces the current to improve efficiency and reduce battery consumption. Second one is controller. So, the controller is the brain of the BLDC drive system. It processes the required torque, rotor position, speed, and current feedback to determine the appropriate switching sequence. So usually there are two major control techniques are commonly used. One is six-step commutation and another one is field-oriented control. So six-step commutation is also called 120-degree electronic commutation, in which two motor phases conduct at any instant while the third phase remains unpowered. So the rotor position is detected using Hall sensors or estimated using back EMF. In field-oriented control, it is an advanced vector control technique that transforms three-phase currents into two rotating reference axes, that is D axis and Q axis. The controller independently controls magnetic flux and torque. So third one is commutation angle, theta. The commutation angle determines when the controller should energize the next stator winding. Proper timing is essential because the stator magnetic field must remain approximately 90 electrical degrees ahead of the rotor magnetic field to generate maximum electromagnetic torque. If the commutation occurs too early, torque decreases, motor efficiency reduces, current increases unnecessarily. If commutation occurs too late, rotor lags behind, torque ripple increases, motor heating increases, efficiency decreases. Rotor position information is obtained using Hall effect sensors, optical encoders, magnetic encoders, sensorless back EMF estimation. So the fourth one is PWM and current control. After calculating the required torque and commutation angle, the controller uh, generates pulse width modulation signals for the inverter switches. For inverter switches means MOSFETs or IGBTs. So PWM controls the average voltage applied to the motor. Current sensors continuously monitor the motor phase currents. The controller compares the measured current with the reference current and adjusts the PWM duty cycle accordingly. So modern BLDC controllers typically use PWM frequencies between 10 kHz and 25 kHz, which also reduces audible switching noise. BLDC motor, stator and rotor side. The inverter applies controlled three-phase currents to the stator windings. These currents produces a rotating magnetic field. The rotor contains permanent magnets, usually made of neodymium ion boron. The rotor follows the rotating stator magnetic field due to magnetic attraction. As each phase is energized in the correct sequence, a rotating magnetic field is produced. The rotor aligns with this field. Continuous rotation occurs. Mechanical output power is delivered to the load. So feedback, usually speed and current feedback is continuously monitored. Uh, Sensors measure rotor speed, rotor position, motor current, battery voltage, and motor temperature. So the measured values are sent back to the controller. The controller compares desired speed and actual speed. If any error exists, it immediately adjusts PWM duty cycle, phase current, and commutation timing. Load matching process. So load matching process is the continuous process of adjusting motor operation to match changing the mechanical load conditions. So the importance of load matching, what we have seen for this past 5 minutes. So these features make with features of BLDC, such as high starting torque, smooth acceleration and deceleration, fast dynamic response, reduced torque ripple, lower vibration, etc., make the BLDC motors ideal for electric vehicles, electric bikes, drones, etc. So, with this, we conclude that here, and we will see in the next video.